started, before we jump into the lecture, at the end of class on Tuesday, I just want to remind you, when you look at the bottom of page 87 in the book, it's got a few different drawings here, and they've mislabeled 2 of them. Okay, so they're calling C the vertical shear and B the bending, but in actuality they have them mixed up. Okay, so if we have our beam and it's supported over a span and we have a uniformly distributed load, if our beam were to fail and the entire beam to move down, so we get this case, this is vertical shear, okay? That's when, the definition of shear is when you've pushed through that entire cross section, right? Okay? If we instead are deflecting and have an increased deflection through the middle of the beam, and we're getting failure in that tension face, that's buckling, okay? So, just be aware of that. So, we walked through one example problem, talked about direct shear stress on Tuesday. So keep in mind, we're dealing with different actions of these forces on our material than when we talked about direct axial forces. Remember that when we were looking at direct axial force, so this is the bolted steel from Tuesday. Remember that when we were talking about axial forces, an axial force would be operating along the bolt itself. Okay, so that's what we just talked about. Here we're talking about shear stress. So shear stress is operating through the cross section of the member, okay? So instead of running along its axis. Does that make sense to everybody, what it is that we're going to be looking at? Okay. So we walked through that problem and determined that direct shear stress. And we want to remember that when we are performing shear calculations, we use either the notation V sub V or V for our shear stresses. Okay, so V is the letter used to denote shear investigation. Okay, so I talked about that. As we're looking at these beams, we will again assume that the self-weight of the beam is negligible and we don't need to take it into account as we're doing this investigation. Okay? So we have a couple examples that we'll look at. These are the examples in your book. I think they're 3.2, example 1 and 2. I'm going to call them examples 2 and 3 because this is truly our example 1. Okay? So the easiest way to look at shear initially is to just look at a uniformly distributed load across the beam itself. And so what we'll do is we'll set up our load. Okay, and so, actually this one isn't from the book, right? They have the point load and then a point load with a, so, do you remember what we need to do to determine first our reactions? What is it that we would want to do? It's our first step that we always solve. We want to make sure that this thing's in static equilibrium, right?
Yeah.
Okay. forces in the x direction equals 0. We do, right? We have nothing acting in the x direction, so we're good there. What about our forces in the y direction?
You have 800 pounds.
What's that?
Well, if 800 pounds in the Y,
800 pounds per foot, right?
It's
So
10 feet.
so that's 80. Do you do that? Is it like, if it's 10 feet long, there's 80 pounds?
wouldn't it be
What would be 80?
It'd be 80 times.
800 pounds per foot times 10 foot,
Yeah.
Yeah.
right? Okay. And do we want to call this negative? It's acting,
Because it's going down.
it's acting downwards.
Yeah.
Okay. What else do we have for y forces?
R1 and
R1
R2.
and R2.
R1 and R2. Okay. Can we solve this currently?
No, there's 2 on them.
We have 2 unknowns, 1 equation, right? Okay. What about moment?
Yes, if you can solve it.
Right? Isn't that the next step?
Yeah.
What would you rather look about point 1 or point 2? Doesn't matter to me.
Doesn't matter.
Okay. So our moment about 1 equals what? How do we resolve these uniformly distributed loads
It's
when
going to be
we're
R.
determining reactions?
Do it right in the middle.
Put it at the midpoint, right? We already know that we have 8,000 pounds. What is this distance?
5.
5 foot. Okay. Is this going to cause clockwise or counterclockwise
Clockwise.
rotation? Clockwise rotation. Does the reaction at 1 tend to cause any rotational effort about 0.1? Nope, that is 0, right? Okay. What about R2?
So it would be R2 times 10.
R2 times 10. Is it trying to rotate clockwise or is it trying to rotate counterclockwise?
Counter.
Counterclockwise, right? So we need to make it a negative value. Okay? So, for the moment, about 0.1 is equals 0. R2, was that 40,000?
No, because it's 800, not 8,000.
What?
No.
Keep in mind, it's 800 pounds per foot,
Oh, okay.
right? And you've got 10 feet, okay? So when
So it's
you,
8,000 in the middle then. You see it?
yep,
Yeah.
yep. So this becomes 40,000 divided by 10, 4,000 pounds, okay? So that will mean that R1 is also 4,000 pounds?
Some of the math is in this is true.
Okay, does everyone agree with those statements? Okay. So now, we can look at how are these forces acting as shear elements. Okay? And what you'll do is step along your beam at various points, and just determine them at a couple of points. Okay? So if we go just to the right of R1, an infinitely small amount of area, and we want to look at the forces that are trying to shear there, what do we have?
We have R2. Are we talking about just from the leftover?
We're looking from the left over.
Will we have the R1 at
R1. Okay?
8,000 pounds?
Do you know our distance as well? So V at x equals 0 equals R1, okay? So your shear force is 4,000 pounds. When we look at shear in beams, we do not resolve it into a point force, into a point load, okay? Because it's going to be acting at all of those elements, okay? So resist the urge to, we need to resolve it to a point load to determine equilibrium, but you don't resolve it when investigating the shear. Does that make sense to everyone? Why that is? Okay. So let's have our next point be, let's look at 1 foot away from R1. Okay? Looks to be about 1 foot, right? If we're looking on the 1 foot left of where we made our cut, what forces do we have acting on the beam in shear? 2 forces, right? We'll still have our reaction. R1 is trying to shear that beam.
Well, then you're gonna have part of the 8,000 force, or 8,000 pounds coming down.
Yep, yep. Then you'll also have your uniformly distributed load acting on it, okay? And we know that it's 800 pounds per foot,
Oh.
so it's going to be
40.
R1 minus 800 pounds per foot times 1 foot. Okay? Does that make sense to everyone as well? So 32 pounds. Sorry, 3,200 pounds. Now, let's look at x equals 6 foot. Okay, so what do we have?
So it'd be R1 minus 800 pound feet times 6 feet.
Okay,
This makes a lot more sense.
so here we have negative 800 pounds. So we should back up and see where does this equal 0? Where the shear is going to equal 0 is going to be very important for us in the next portion when we get done talking about shear, when we talk about bending. Whenever you move from a positive to a negative value in shear, at that point where your shear equals 0, that is when you will have maximum bending. Okay, and we'll talk about bending. We may not get to it today, we'll
At
see.
0
So
is
would
where
there be
it has
5,
the
since it's all equal, you know what I mean? It's
Yep.
right in the center and.
For this particular example, yeah,
Right.
it would occur at 5 feet because of the loading that we have. Okay? Last, let's look at x equal 10 foot. What is happening there?
You're having the whole 8,000 pounds. I mean,
What's that?
R1 minus 800 times 10.
What else would we have?
What would you have?
You'd have R2.
We'd have R2 as well, right?
So where does that go in the, does it go at? Oh, it's plus R2 at the end.
Yep. Okay.
So we get 0 in the middle and the end?
Yep. What would we have just to the left of R2?
399. Negative.
What'd you get, Russ?
79.20. It would be negative 79.20.
This value, right? Yep.
Yeah. But you would take 4,000 out of that, way. Yeah.
Yep. Okay.
If you're cutting right there, why won't you use R2? Oh, are you going? Oh,
Saying
okay.
we're just left.
Oh, we're just left of
We're
it?
just
Okay,
left of
so,
that beam.
alright,
Okay.
I got you.
So you did, for 10 feet, why did you change it to 8,000 pounds?
Why are you doing 800 at 8,000 something?
Oh, sorry.
One above it, there you go.
Okay.
It was just incorrect. Incorrect writing. So where is your maximum shear occurring?
Right before R2, or right before the middle.
At the reactions, right?
So you want what, the biggest big number and the smallest negative? To,
Why
Say-
wouldn't it be?
Say that again.
so you want, there are two ends, so you want the
Yep.
lowest negative and the highest positive?
Not necessarily. We have to keep in mind the magnitude doesn't care about the sense, right? Over here, the shear force is acting in this direction, right? Over here, the shear is acting in this direction.
Right.
Does the beam care in which direction you're trying to shear it?
No.
It just cares how much magnitude you're trying to shear it with. Does that make sense to your question? Okay, so in this particular example, because our reactions are equal, the maximum shear occurs at both reactions. Okay? The next problem we'll look at, where we have a couple point loads, we'll have different magnitude reactions, and we'll see that the larger reaction is where your maximum shear will occur. Okay, so go ahead.
The answer to that question would be the maximum shear would be 4,000 pounds at both R1 and R2?
Yep.
That's just,
Yep.
that's what you're asking?
Yep.
Okay.
That's what we're looking to determine. Because remember, once we know,
So
We're less
basically,
cons-
so all of this right here, finding the shear, is to rule out that, or just to figure it out, basically, right?
yep. Remember that we need to know the maximum,
Right.
right? At the point where, if we design our beam so that it has a capacity of 4,000 pounds of shear resistance, is it going to have an issue when it has 800 pounds of shear? Is it going to have an issue when it has 3,200 pounds of shear? Okay, so the whole purpose of the analysis is to step through your beam, determine where your maximum shear is, and then you can design the beam from there.
So,
Okay?
like, do you have to do that for every foot? Like, so would I have to do that 10 times then? For
No,
how many?
so if you're dealing with a uniformly distributed load, I would check it at least 2 points. I think that's typically fine. Yeah, Jim?
Are you always doing it from the left? What's to the left, or can you do it from the right?
You can do it from the right if you want.
You just have to keep it.
Just be consistent.
All right.
Just be consistent with what you're doing, right? If we looked at it going this way, wouldn't we get the same things, right?
Since it's equally distributed, yeah.
Yeah. If we cut it just to the left of R2 and looked only at the right-hand side, what would it be here? What would your magnitude be?
With that?
It'd be 4,000, right? It would just be that. As you move a foot over, what are you going to have?
You're gonna have that 3,200 pounds.
Then you're gonna have 3,200 pounds, right? Because you'll have your reaction at 4,000, and you'll pick up 800 pounds per foot, okay? So as long as you're analyzing the same load distribution and you don't change any of the dimensions on the beam, regardless of if you investigate left to right or right to left, you will get the same answer, okay?
Well, seems easy enough,
Now, but
but
let's
sure, we're
do,
about to go down the rabbit
Should
hole.
we,
let's do an
should
uneven
we
one.
complicate things?
No.
Well, let's do one where they're not equal.
Let's look at
Brand new?
a truss where we have 2 point loads, okay? I'm sorry, not a truss, a beam. And they have already determined the magnitude of the reactions for these guys. So we have 1,000 pounds at our reaction at point 1. And we have 600 pounds in our reaction at point 2. We have two loads. Halfway.
That's what they have.
And in this case, they're point loads. So we have a 600-pound force being applied 2 feet from R1. Sorry. And we have a 1,000-pound force. And the 1,000-pound force is 6 foot from both of the reactions. Okay? So overall length of the beam is 12 foot. And now we can start looking at the shear. Okay? Do you want to work left to right or right to left?
Left to right.
Left to right?
Should be the same.
It'll be the same either way. Yep. So if we cut our beam and we make it an infinitely short distance to the right of R1, what do we have?
1,000.
We have 1,000 pounds, right? Look at next. If we go 1 foot away, what do we have?
1,000.
So it'd be 400?
We're 1 foot away and we're looking to the left.
It'd be 400 pounds.
6.
Is there anything being applied up here?
No.
Just
No, because it's
1,000
not-
pounds, right?
So that's at that
because it's not-
point
I got
loads
you.
at 4 feet, right?
Yep. Next, we'll look at 2 feet away. Okay. Now what do we have?
R1.
R1 minus 600.
R1 minus 600. 400 pounds. Okay? If we look at 6 foot, what do we have?
R1 minus
1600.
1,600.
Minus 600 pounds, right? Okay. And then if we look at an infinitely short distance away, when we're at the end of the beam, what would we have?
Sure you want to call it 10?
Yeah. We'll call it 10.
Okay. Isn't 10, so the 10 would represent 10 feet?
Yep.
Okay.
Sorry, no, you're right.
12 feet.
I don't want to call it 10.
Yeah.
Because you wanted the end,
It's a
right?
12-foot beam,
Okay.
right?
So it'd be equal R2.
Yes, sorry. So this one will be R1 minus 600 plus 1,000 plus R2.
What would it be plus 1,000?
Do you like to do
I just
that
got 'em.
instead of-
They're just all in the
Minus
parentheses.
1,600?
You gotta just do crazy math, don't you?
Yeah.
So what does it equal here?
0.
600.
0, right?
What is an R2?
There's 1,600 here.
So you get negative
16.
600
Oh,
plus.
okay, yeah, I got you.
So in this case, where does our maximum shear occur?
I'm gonna say 5.
R1.
Oh, yeah.
R1, right?
Yeah, I was thinking about 0.
Okay. Because we don't have a uniformly distributed load in this case, we won't have anywhere where we'll have 0 shear, right? Here it has a value of 400, here it drops over to negative 600, okay?
Isn't
So there's
12
not a way
feet
to
zero?
find 0 in between there?
Isn't R2 0?
Because
You
it
just-
crosses
Isn't
the
12
0
feet at
goes
0 though?
negative, so it has to
Yeah.
happen somewhere. Right? So you got 1,000 pounds,
0 shear at R2.
and then at 2 feet, you end up with 400.
Is that-
But then at 6 feet, you had negative 600, so it has to have 0 at some point.
You go all the way to the right, just turn right, is it gonna be?
It just jumps to negative.
Yeah,
We'll get to shear diagrams in a moment.
but isn't it, at R2 we just figured out it was at 0, right? Or at 12 feet,
Yeah, but-
so.
Now you catch,
That's because we're looking from left to right.
Oh, we looked from.
If we go backwards, if we go right to left, what would you get here for your shear?
Sure did.
The 600 pounds.
600 pounds,
Okay, yeah.
okay? So it's going to depend on how you're looking at the beam.
So let me ask you something.
Yep,
So from 2 feet to 5.99999, 600 pounds is, or 400 pounds would be the force, and then at that single second, it
Yep.
jumps.
that's where it's gonna jump, okay? So that's where, when you make that jump from positive to negative, that's where your maximum bending will occur, okay? In the case of a uniformly distributed beam, it's going to occur where the shear equals 0. We
Okay.
don't have uniform distribution here, right?
So it'll happen at the heaviest load.
Uh,
Well,
no. It's going to happen when it moves from positive
to,
to negative,
okay.
So
okay?
you don't say there's 0 shear at R2 because there's support there, basically, because it's not part of the beam, or what?
No, because if, that's only because we're looking at it from left to right.
We're just
If
looking at it from left
from
to
right
right.
to left, it would be 600 pounds there.
Okay.
So all you're doing is getting back to your equilibrium condition, right? If we looked at it right to left, so make an infinitely small cut there, right?
R2 would be 600.
Right.
V of x equals 12, now equals 600 pounds, okay?
So
Alright.
I'm just looking forward to like problem wise. Are you looking
Let's
us?
go out there and-
What are you looking for us to solve? Just like that right there, or like are you trying to make us determine something?
You read my mind.
I would ask you to do shear calculations going in one direction.
And
And
determine.
knowing what you know, that the shear occurs at the maximum, at the larger reaction, I would begin your analysis from there, okay? Because that's going to give you your maximum shear.
And that's what we're looking for. Is this maximum shear?
Yep, it's all we care about with shear.
Okay,
is
that's-
what is our maximum shear, right? And again, keep in mind, the beam doesn't care if it's 600 pounds shear this direction, it doesn't care if it's 400 pounds shear in this direction, right? All that matters is the magnitude. The sense is immaterial to our beam, okay? Yep.
Are we ever gonna look at like angular forces, like coming down on? Like,
We won't look at angular forces, not for the purpose of this analysis. You'll either have a point load or you'll have uniformly distributed loads,
Okay.
so. Okay, so now let's look at the case where we combine the two.
The E.
It'll never be true.
So now we'll have a beam
Right. I need to make a pencil like that on the break.
You gotta lift your weights, dude, your jaw.
One. Here. Okay. How
Okay, so we know our reactions. We have a 12,000 pound load, 6 feet from R2. And then we have a uniformly distributed force of 800 pounds per foot. Okay? So first let's look at Vx equals 0.
You have 10,900.
Are we going from R1
We'll
again?
go from R1 to R2.
Well,
Yep.
shouldn't we go from R2 to R1 since that's the larger force? From what you just said, like a couple minutes ago?
Sure, if that's what you want to
I
do.
don't like change.
Well,
that's what we
that
wanna
makes
do.
most sense to go for the bigger force.
We can also, remember what happens when we make that cut just before it too,
Mhm.
right? Okay,
10 R2's not there.
what's that? No, we can't pretend R2's not there. That would get us in trouble. So if we look at making a cut just to the right
We have
of R1,
at
the
10,000.
R1.
R1 equals 10,900.
So are we using going from the left or right?
Thank you.
what?
Which one are we going from?
Left or right?
Started right.
Okay.
I'm gonna rewrite it right now.
What happens 1 foot away?
You have
Nothing.
still the R1, but then you have
What?
50 pounds.
No, it'd be
800
10,100.
pounds.
10,100, yo.
800 pounds times 1 foot plus 10,900.
Would it be plus?
Yeah, so you have 800 pounds plus the 900.
Because it's 800 pounds per
Oh, 'cause
foot.
it's adding on it, okay.
Because we're doing both, not
Okay.
just point.
Right?
Yeah.
10,100 pounds?
Sweet, yeah, that was
Is
right.
that
It is minus.
minusing it?
Ah!
Yeah, because it's a negative 10,900 is a positive.
If we're calling this positive, doesn't the sense of this have to be negative? Because they're going in opposite directions, right?
Is that 2 or 1? 2,100?
10,100.
This is a poorly drawn one. Sorry. If we make a cut 5 feet from R1, what would we have?
So it'd be
Uh,
10,900
It'd be
minus 4,000.
800
800
pounds
pound-feet
times 5.
equals, that's 4,000, so it'd be 6,900.
6,900 pounds, right? If we look at 10 feet,
That's
but we're just to the left of the force of the point load, okay, so we don't take it into account,
Mhm.
what would we be looking at?
2,900.
Yeah, pretty much. So 1 minus 800 pound-feet times,
2,900.
yeah.
2,900 pounds. Now, if we look just past the force, but we're still at 10 feet, what would we have? So V equals 10
14,900.
plus.
14,900.
Yeah, it's same thing, but then you subtract another 12,000.
No, you add that.
No, you subtract 12,000.
Subtracted.
Because it's 10,900
It
is
was going up,
positive.
yeah.
Yep, keep in mind what the sense is
Yep.
on your forces, right?
So 2,900 minus 12,000 pounds
So
is
negative.
negative.
Okay? What does that tell us about this point?
That's
It's our max
our
shear so far. Probably total.
no. It's not our max.
Is
It's
it your
like
max shear?
no, but it's
No,
the
it's
point
What
where it
did we
bends the
do?
most.
We had our inflection point, right? We
Yeah.
moved
your
from
maximum
positive to
bend.
negative.
Yeah.
Maximum bend, yeah.
The maximum
So
bend.
that will be where your maximum bending will
That's
occur.
what I meant.
Okay. Now if we look at, we'll call it x equals 16, but we're going to look just to the left of R2, an infinitely short distance. We're so short, we're so close that we're 16 feet away, but we're not close enough to pick up the reaction, okay? Now what's occurring?
This would be 100 pounds.
What? What would we have for a uniformly distributed load?
Yeah, 800 pounds.
800 pounds per foot?
Plus.
Why would it be plus 1,200? I swear to God. we just-
12,000.
whatever.
I just,
Because you're distributing the
Oh,
number
because
one.
you gotta
yeah, I'm just keeping them all in
do that crazy
parentheses.
math again.
Just right now.
13.9. So you're right at R2.
Okay,
Top of R2.
yep. So that's how we will combine the beams, okay? So you can say that you're all the way across that beam, but you're infinitely short distance away so that you can ignore that reaction, okay? So, what is the maximum shear force exerted on the beam?
13,900 pounds.
13,900 pounds, right? Our maximum reaction. This is what you would want to report, okay?
Cool.
You don't have to
So-
say that it's negative or positive.
Since they give us the reactions, we already know, we don't have to do all the math, we know just by looking at it that 13.9 would be the maximum because it's in equilibrium, right?
Yes, you may assume that if you are given the reaction forces, that you know that the beam is in equilibrium, okay?
Yeah.
All right? Questions on these types of problems? These seem that you'd be able to do them if they were presented to you as homework?
Better.
Okay.
I like this better than triangles.
Yeah. This is going more kosher.
This is division one. Yeah, I can do that. How many more classes is there?
So that takes care of the vertical shear. The next thing we need to look at is a shear diagram. Maybe we'll be able to start talking about bending just a little bit today.
It's like Friday, man.
Is that it?
It's Friday.
It's Friday.
We're only taking so much knowledge at once.
Yeah, it's
Friday.
We can take this data and generate a diagram and show what this looks like over the span of the beam. And that's really going to be more valuable for us than just putting all these numbers up on a page to help us, because while it's important to know the shear, the maximum, the shear diagram will ultimately help us draw the bending lines, okay? And so when we're going into these designs, we need to take into account axial stresses, we need to take into account shear forces, we need to take into account bending when we size our beams, okay? So it has to be able to meet all of those conditions. And we can generate the bending diagram from our shear diagram. So what we'll do for these problems is you'll draw your beam to scale, okay? So we can use our last example here.
Let's put NTS on there.
So 10,900 pounds. Over here we have 13,900 pounds. Assume that that's a uniformly distributed load. Same distance at all places. So 800 pounds per foot. And here we have our 12,000 pounds. To draw your shear diagram, you'll put underneath your beam itself a horizontal line. Okay? It'll have the same distance, 16 feet, as your beam, in this case, as your beam. And what you'll do is you'll just plot your points. Okay? So here is 10,900 at x equals 0. At x equals 1, we'll have 10,100. Okay? And then just continue stepping through the beam itself. X equals 5. Let's see, so we're halfway here. Be 6,900. Will be 2,900 and minus 9,000. Ending at minus 13,900.
So you just kind of guesstimating where.
When drawing these, your linear scale will come in handy here, right? To help you scale things. From there, it's just connecting the dots. Okay? So this is the shear diagram profile for a beam itself. If we only had, well, let's just throw it up for the other one. Do the shear diagram for the point loads. Full scale. Okay. So here we would have, at 0 we had 1,000 pounds. £400. True. Okay. If you have only point loads, your shear diagram should look like stairs, right? In between these points, we are not changing the shear at all, correct? There's no further forces acting on the beam itself. Over here, we have a slope. And this slope should be 800 pounds per foot, right? Because that's taking into
So is
account.
it the only reason we have the straight drop off because we have the point load there?
Yes.
Okay.
Yep. That drop off, just like here. So, the location of your stairs, right? That's going to represent any point loads, okay? This represents that we are not increasing, nor are we decreasing our shear between these points, right? This tells us that we're increasing and decreasing, those points. Okay? Seem reasonable? Seem achievable for everybody? Okay. Well, we're a little early, but I prefer to stop here and give you the homework on the shear that you can work on, and then we'll pick up bending on Tuesday. Does that work for everybody?
Yes.
I'm down with that.
All right. It'll be posted
So is
here.
Bending like a big deal.
What's that?
Is bending a big section?
We'll do about the same amount as we're doing with shear. I don't want to tie up ourselves with a bunch of times. So we'll look at the bending, and then we'll look at buckling.
Okay.
That'll kind of be it. Then we get into chapter 4, where we're actually bringing everything together and actually start looking at systems,
Okay.
combining all the forces and start solving and figuring out how to size things.
No more math.
Oh no. It will still all be math.
Yeah, sign up for this, man.
You absolutely do. What are you talking about?
Not knowing.
I was under the
This is now
understanding
like
of when I went through
7
math, that was gonna be it.
Yeah, so it'll be problems 3.2 A through S in the homework is what you'll have.
You'll post it online.
Yep, I'm gonna throw it up here on mine for you. So wrestle with them over the weekend, come with questions on Tuesday.
Okay.
We'll knock it out from there.
Pretty good.
You already done, you okay?